Building America program. We are excited to have Andrew Porschke and Anthony Grisolia here to discuss low-load HVAC systems for single and multifamily applications. Before we begin, I'd like to quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio pane. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio pin that you should use to dial in. Panelists, we ask that you please mute your audio device when you are not presenting. If you have technical difficulties with the webinar, you may contact the GoToWebinar help desk for assistance. If you would like to ask a question, please use the questions pane to type in your question. Please indicate which speaker you are addressing your question to as well. If you are having trouble viewing the materials through the webinar portal, you may find PDF copies of the presentation at the website listed here, and you may follow along as our speakers present. The associated case study is also posted there. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting program prepared for you today that will discuss current research on comfort in residential buildings. Results will be presented from 37 new homes that were monitored in the Southeast United States. The presenters will also discuss results from a modeling exercise that identified the impact house design, system design, and control strategies can have on comfort and energy consumption. Ibicus has begun investigating a plug-and-play duct system that is intended to significantly simplify the design and installation process of ductwork, as well as reduce the risk that poorly installed ductwork will hamper performance. Finally, Ibicus will discuss the differences in performance of a standard system, a small diameter system, and a ductless mini-split system in a new set of construction townhomes. Before our speakers begin, I will provide a short overview of the Building America program. Following the presentations, we will have a question and answer session, closing remarks, and a brief survey. The U.S. Department of Energy's Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for 20 years. The world-class research program partners with industry to bring cutting-edge innovations and resources to market. Visit our website at buildingamerica.gov to find more information about the program and the Building America Solutions Center, which provides expert information on hundreds of high-performance construction topics, including air sealing and installation, HVAC components, windows, indoor air quality, and much more. Building America is supported by 10 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. And now, on to today's presentation. Our webinar today is High Performance HVAC Systems Part 2, Low-Load HVAC Systems for Single and Multifamily Applications. If you would like more detailed information about this effort, please feel free to contact our speakers. Our first speaker today is Andrew Porschke, a Building Performance Specialist at Ibicus. He conducts research in building performance for Ibicus. He uses his experience in sensors and monitoring hardware to design and implement remote data acquisition systems to monitor test buildings, and analyzes the performance of HVAC systems using test house measurements to calibrate transient thermal models. He is proficient in advanced computational analysis using the latest statistical software packages, which he uses to analyze and visualize large data sets in new and insightful ways. Andrew is also involved with product innovation for major manufacturers at Ibicus, testing new systems and evaluating their performance against established metrics. Andrew previously assisted in the commissioning of the Eco-Commercial Conference, located on Bayer's Pittsburgh campus. He is a graduate of the Pennsylvania State University, where he studied energy engineering and participated in the 2009 Solar Decathlon. Our next speaker is Anthony Grisolia, who is Director of Product Information with Ibicus. He oversees Ibicus consulting activities and services for product and material manufacturers, including technical services and testing for existing products, development of new products and markets, and evaluation of product opportunities. Anthony also helps support production home builders, having evaluated hundreds of residential construction issues and performed construction quality assessments with builders in 40 different markets. He acted as principal building scientist for the construction of DIY Network's Best Built Home and regularly develops specifications and conducts quality assurance for green communities. In 1999, he was honored with Canada's Energy Efficiency Award for an energy efficient housing design. Anthony has a Master of Architecture degree with an emphasis on sustainable design from the State University of New York at Buffalo and a Bachelor of Building Science degree from Canada's Ryerson University. With that, I'd like to welcome Andrew to start the presentation.
All right, hello there. This is Andrew Porschke
and Anthony Grisolia.
And yeah, thanks for joining us today. Today we'll be discussing low-load HVAC systems for single and multi-family applications. Got our agenda here. Today we'll be going over some of the research that IBACUS has done in the last year, investigating the performance of HVAC systems specific to low-load homes. We'll talk about a large-scale study where we monitored 36 homes in the southeast. We'll talk about a modeling study where we did a large number of energy models to look at the comfort of some different systems. We will be reviewing a case study where we compared the performance of a small diameter system to a traditional duct system in a townhome, multi-family townhome. And finally, we'll review some of the results of an effort that we're conducting to develop a plug-and-play duct system. And then we'll discuss where we're going with some of this. So first, we're going to jump right into the data from this study of 36 homes. We monitored the temperature and humidity in all of these homes in the significant rooms in the house. So we put about 5 sensors in each home and collected data over about a 2-month period. All of these homes are located in the U.S. Southeast, in Tampa and Orlando, as well as San Antonio and Houston. So we monitored all of this data to get an understanding of some of the current state of the performance of new homes. All of these homes were built in the last few years, and they were built by home builders promising high performance and also offering a comfort guarantee on their homes. And so because these houses had a comfort guarantee, we were working under the assumption that the occupants would in fact be comfortable. So we could go in, take these measurements, review the data, and start to get an idea of different circumstances in which people are comfortable but might not necessarily align with industry expectations of comfort. And just to give a quick overview of what you're seeing here, again, this is all of the data from all 36 homes. We're plotting the actual temperature measurement, and you'll see that time is on the horizontal axis, and we're actually plotting each temperature measurement on the vertical axis grouped by the home. And I'd like to just point out a few homes here. This home 24, 25, and 26, these homes are all located in the same neighborhood and on the same street. And you actually see pretty different temperature patterns in those homes.
And they were all built to the same energy efficiency code, 2012.
Yes, they were all built to the same efficiency code. The only difference in these homes are the occupants and their behavior. In home 25, you can see that the temperature is relatively consistent over time. However, home 24 and home 26, you can see some different behavior, perhaps an automated thermostat setback. So we're starting to understand a little bit more about what occupants are actually doing in their homes. So to step back for a minute, I just want to talk a little bit about how IBACUS thinks about comfort. Comfort in general is a subjective feeling of satisfaction with the thermal environment, but everybody has a slightly different idea of what that satisfaction might be. And so what we found is that looking at not as much specific temperatures, but to look more at temperature uniformity across the home, gives us a better understanding of comfort and a more quantitative way to diagnose potential comfort problems between homes. So some of the specific numbers we'll be talking about today are drawn from ACA Manual RS, which discusses comfort in homes. And that manual says that each room in a home should be within 3 degrees Fahrenheit of the thermostat during the cooling season and 2 degrees within the thermostat during the heating season. And along with that, then every room in the home should be within 6 degrees of the other rooms during the cooling season and 4 degrees during the heating season. So we'll keep coming back to this room-to-room metric where perhaps the top floor is at a warmer temperature, the bottom floor is at a cooler temperature. But according to ACA Manual RS, they should be within 6 degrees of each other. And one other metric that we will discuss is related to ASHRAE Standard 55, and that's temperature uniformity over time. According to that metric, the temperature in a room should not change drastically in a short period of time. And for example, it states that in a 15-minute period of time, the temperature should not change by more than 2 degrees Fahrenheit. So we'll keep coming back to these numbers, but I just wanted to give a quick intro so that you're familiar with them. So we're going to start with actually looking at ASHRAE Standard 55. And these are the same 3 homes that I highlighted before. These homes, again, are on the same floor plan. It's the same street, same orientation. The only difference is the occupants. And so what we did was select data from 3 days in September and plotted it on a psychrometric chart. And as well as doing that, we drew the ASHRAE Standard 55 comfort box onto that plot. And that box is representative of an occupant wearing typical clothes. It's a 0.5 clothing value, and that assumes pants and a long sleeve shirt and a 1.0 MET rate, which is a metabolic rate. And that's pretty standard for somebody who might be sitting in their home and not doing any active physical activity. And so what we found when we started plotting data on one of these charts was that there's a wide variety of preferences within a home. So again, all of these occupants, we're working under the assumption that they are comfortable. They have the ability to set their own set points. And if they decide their home isn't comfortable, they've had opportunities to get that fixed. And so what we found is that, for example, in one home, the rooms are within that box 77% of the time, and another home, the rooms are within that box basically 0% of the time. And so there's this wide variety of temperatures that people think are comfortable. In one case, the average temperature is around 70, maybe 77, and in another case, the average temperature is around 72. And these people are neighbors. So we've really found that there's a wide variety of expectations for comfort. So let's look at all 36 homes at once. And what we've done here is selected the data for the entire month of September for all of these homes. Again, they're all in hot and humid climates in the southeast, and they're all relatively new homes. And what we found is that according to, again, the ASHRAE comfort box, that the rooms in that home were only within the comfort box 47% of the time. And that actually the median set point, if we're just looking at the thermostat temperature, the median set point was 75 degrees. So people, at least in this climate, in these homes, seem to have an expectation of comfort that's somewhat different, perhaps, than the assumption. So now to change gears a little bit, we're going to discuss comfort according to ACA Manual RS. And so again, in this plot, we're looking at all 36 homes for the entire month of September. And what we've done is calculated the room-to-room temperature difference at each time step, and then done a cumulative summation of that over time to understand the total percentage of data that lies within a certain temperature band. And so, for example, what we see here is that 95% of the time, so this green vertical dashed line, the maximum room-to-room temperature is 6 degrees Fahrenheit or less. So the closer this blue curve is to 100%, basically represents the majority of the data being under that curve. And so the ACA threshold is 6 degrees. And again, what we found was that these homes, according to the ACA threshold, were comfortable 95% of the time. And so the next question then is, how does that relate to a home builder? The home builder is interested in understanding their potential risk of comfort callback. That's when a consumer is uncomfortable in their home and they either call the builder or the HVAC contractor, somebody has to go back to the home and fix things, and that ultimately costs them money.
Yeah, so from a builder's perspective, we get these questions a lot where we get comfort complaints on a specific building, and we're trying to understand, is the ACA standard actually valid enough? Because we get we hear builders complaining about homeowners being uncomfortable when there's a 3-degree difference instead of a 6. So we're trying to understand where is that point in time where there's a lot more risk for a builder. Is it 3 degrees, is it 6, or is it 10? So we're trying to understand that from a lot of this data that Andrew's been presenting so far.
Yeah, so we don't necessarily have the answer to that yet. And I think, from a builder's perspective, it would be great if they could understand, yeah, this home has, the way it's designed, has maybe a 5% risk of getting a comfort complaint, whereas a different design that's maybe not quite as well performing might have a 10% risk. And we don't have the data yet to fully fill in this picture, but it's something that we're interested in and somewhere we think we're going to be able to understand comfort in homes. So continuing with this same data set, and I just want to show a couple more interesting things we discovered. We really wanted to dig into some of the potential factors influencing comfort in these homes. And so whenever we installed the sensors in the homes, we also did a brief survey of the occupants to understand things like, are they full-time employed or are they part-time, to understand, for example, whether or not they use a programmable thermostat and whether these factors might influence comfort in their home. And what we found, at least with these two factors, was that there wasn't a significant trend that, perhaps just depending on their own lifestyle, even if they were full-time or part-time or retired even, that the room-to-room temperature in that home depended on many other factors. So one of the factors that actually had the most significant impact was the number of stories. And this is to be expected. You have a 2-story home, you're going to get more temperature stratification. And we found that the room-to-room temperature on average was 3 degrees Fahrenheit for the 2-story homes, whereas it was only 2 degrees Fahrenheit for the single-story homes. So there's a little bit more evidence showing that the more complex you have a building design, there's a little more risk for comfort issues. One other thing that we monitored in this study was the humidity in the homes. Now these homes, again, were in a humid climate. However, they did not have any active dehumidification. There were no dehumidifiers or any other supplemental equipment. It was relying purely on the installed centrally ducted HVAC system to provide dehumidification. And so looking at this plot, any of the areas that are shaded magenta represent periods of time when the humidity was above 60%. And what we found was that there were really only a few outlying cases when humidity was to that level. We're just speculating about some things. For example, in one of the cases, this home 2 that we've highlighted, that home was very similar to homes 1 and 3. They were in the same neighborhood, same builder. However, home 2 had a gas stove, whereas the other homes had electric stoves. So one possible source of humidity in that home, and it might have made all the difference. However, in general, what we found was that humidity levels were able to be maintained at an acceptable level, which is something that we found to be interesting and perhaps a little bit unexpected in this very humid climate, especially considering the data that we're looking at is also during the beginning of the shoulder season. October, the system isn't running as much, but there wasn't a major humidity problem. So to recap some of the key lessons learned, comfortable occupants aren't necessarily the same. People have different expectations, different preferred temperature profiles, and you really have to look at a variety of preferences when designing your home to provide the best comfort to everybody. Room-to-room temperature uniformity is a better metric, perhaps, than looking at a single temperature band. That way an occupant can set their thermostat to whatever they want, and we can still understand how the home is performing. And as we said finally there, humidity actually was maintained below 60% the majority of the time, even without any supplemental dehumidification. So now we're going to change gears to the next project that we're going to discuss. So that first project was really to understand in the field, in the real world, in homes that are being built today, what kind of conditions are people experiencing. Then to kind of extrapolate some of that knowledge to different climate zones, to different house types, to different HVAC system types, to understand the impact of different control strategies, we conducted a modeling exercise using a total of 99 models, and these were transit models, multi-zone thermal simulations, so that we could understand the temperature in each room and the impact that these different factors would have on the temperature in each room. And so we also then used a CONTAM model to help us understand the impact of airflow between the rooms. Because we're really looking at systems, we have to be very accurate with airflow. So we chose to use a CONTAM model as well. So a little bit more details about these 99 models. Each of the homes was built to the appropriate zero energy ready home standard for that climate region, which is very similar to IECC 2012. The three different systems that we studied were mini-split ductless heat pumps. We studied a traditionally ducted central system, and then finally a small diameter system. And then we also looked at 5 different control strategies. We looked at the standard, single zone, single thermostat. We looked at, well, what if you put an additional thermostat into that home in perhaps the second floor? What kind of impact do you have there? So we had a single zone, but 2 thermostats that could turn on that virtual air handler. And then next we looked at a zone system where perhaps you had 2 zones and 2 thermostats to give a little bit deeper level of control. And then the last 2 control scenarios involved running the fan during periods when the system wasn't calling for heating or cooling to understand the impact of perhaps continuously running your fan on comfort. The final case, the model actually made some decision whether or not it thought that there was a potential for a comfort problem, say during a very sunny day during the shorter season, and it kicked on the fan during that period to see if it had much impact. And then finally, you see the pictures of houses that we actually based these models off of. So we based each of these 3 house geometries off of real-world homes that we've studied. And we picked 3 different house types. One of those was a single-story home built on a slab. One of those homes was a 2-story home built, again, on a slab. And then the third case was a 2-story home built over a basement. So this way we would have a variety of geometries and also a variety of window orientations and window areas to again better understand the impact on comfort from these various design decisions. So in this slide, we're showing the results from all 99 simulations. So what we actually did was calculate the room to thermostat temperature difference. So if you'll remember, that should have been within 3 degrees during the cooling season and within 2 degrees during the heating season. So we've calculated that difference for the entire year-long simulation, and then we've tabulated those numbers as a histogram to understand, how tight are those rooms. In an ideal scenario, all of the temperatures in each of the rooms should be very closely aligned with the thermostat. And actually, in this first case of the single-story ranch-style house in the Orlando climate zone, we see that there's a relatively tight clumping around the center. So something else that we've done is then counted the percentage of time that all of the rooms are within that plus or minus 3 degree or 2 degree band. And we were looking at those numbers, and what we actually did was highlight in green all of the cases in which the home was comfortable by that standard at least 95% of the time. And so you'll see that, in some instances, the home, across this vertical column, so the vertical column represents one home in one climate zone, and we see then the impact of different HVAC systems and the impact of different control strategies. And what we see from this graphic here is that in general, the simple floor plan was the easiest to condition. And that's what's to be expected. If you have a simple floor plan, you don't really need that 2-zone system. And there's really not a significant performance difference between the mini splits and a centrally ducted system. Across the board, then, we find that in other cases, the mini splits do perform better. When you have multiple stories in which you might have temperature stratification, or if you have different zones that have perhaps more glazing or less glazing, it's very important to have that zoned approach in which the HVAC system can respond to the unique load profile of the room. One of the things that we thought was interesting was that the continuous fan mode, we thought that across the board it would significantly improve comfort. We're mixing all of the air within the house. It should provide a much more uniform temperature. And in some instances, it did. That 2-story home over a slab, it actually did improve the comfort. But in another case, that 2-story home built over a basement, it actually reduced the comfort in the home by a few percentages. It reduced the amount of time that those homes were within the comfort band, which was something unexpected. And I think the big takeaway from this study was that there really is a strong relationship between your architecture of your home, so the geometry, the way that the rooms are laid out, the way that the windows are laid out, and the system that you ultimately decide to put into that home. And with a low-load home, you have to be very careful in designing your system such that you don't encounter these types of comfort problems. So just to zoom in a little bit more on that data, we've actually excluded the small diameter system from this particular data set. We found that the model didn't significantly capture differences between a traditional system and the small diameter system. And so we're just going to zoom in to really look at the impact of these different control strategies. And sorry, let me jump back. Yeah, so we found that in some cases, for example, in Orlando, the model showed overheating because the climate there isn't nearly as cold as these other climate zones, Fresno and Denver. And so the home actually warmed up because of solar heat gains in the winter, up to a temperature beyond the thermostat deadband, but it was still below the cooling deadband. So it looks like it's an uncomfortable period, but it's likely that an occupant in there wouldn't be uncomfortable. But what we were able to find by looking at the data separated out according to time of the year was that in some instances, you really needed to perhaps rebalance the system to provide optimal comfort during different times of the year. Now that's a challenge with a lot of currently installed systems, that there might not be access to balancing dampers. If there are balancing dampers, maybe they're set once and sealed off in a cavity. And with these low load homes, you just have different profiles at different times of the year. And it's really, really highlighting the need to be able to change the airflow to different rooms at different times of the year. So one of the things we did here was actually plot the temperature data on a floor plan for one of the homes. So this home is the two-story home built over a basement. We see on the bottom, in each of these cases, we see the second floor. On the top is the first floor. The white box represents the garage. This was an unconditioned garage, and we chose not to include the basement in this particular plot, just to put focus on the occupied spaces. And so what I've done then is pooled out 4 specific cases to really look at the impact of these different control strategies. Again, this was the two-story house built over a basement, and this the data in here is from the Denver climate zone. And so if you look at our timer, we're starting to look at data starting in July. So this is the summer. And we'll see as the day begins, the system starts to cycle, and you have all these various cycles, and you start to see that some systems are performing better than others. So when the sun comes out, we see that the southern bedrooms in some cases are starting to heat up significantly. And in the case of one zone, one thermostat, the top floor is actually significantly overheated, whereas the bottom floor, that thermostat is only sensing the temperature in that bottom floor, and it's still quite comfortable. And so if we then consider the case where we decided to put 2 thermostats connected to that one central system, so the box on the bottom left, we see that southern bedroom and the second story in general is at a more comfortable temperature, but what's happened is we've overcooled the bottom floor. That bottom floor didn't need any cooling energy, but it was still supplied. And so in this case, what works the best is actually a scenario with 2 zones and 2 thermostats to provide optimal comfort. And you see that the continuous fan scenario didn't significantly improve the comfort in this particular case. In a different case, it did, however. And then briefly, we'll again look at this similar animation in the winter, and we see again that southern bedroom tends to overheat during the middle of the day when you have strong solar radiation. But we'll jump back to that period. And in this case, there's really not a significant difference between the different control strategies. That again, the continuous fan, yeah, that one room is starting to overheat, but the continuous fan didn't make a significant impact in mixing that home. So some of the lessons learned from this modeling exercise is that, considering the architectural design and massing of the home is crucial whenever you're conducting the HVAC design, especially in a low-load home. That something that works in one home, great, might not work well at all in another home. And at the same time, with simple homes, you don't need a super complex control strategy, perhaps. That with good design, with overhangs and good shading, you can actually provide great comfort using a single zone, single thermostat system. So you really have to consider all of these elements simultaneously to maximize comfort. Again, so window orientation and the percentage of the window relative to the wall area is a significant factor. In some of these cases, 2 thermostats were necessary. And actually what we found was that in some cases, it makes more sense to put one thermal zone on the southern side of the house and one thermal zone on the northern side of the house. Typically, a 2-zone system might be the top floor and the bottom floor, but that might not always be the best case to maximize comfort. Something else that we noticed was that in climate zones with large temperature swings between the day and the night, like Denver or Fresno, there's actually an opportunity here by increasing thermal mass, perhaps to improve comfort. So to bring this back again to the real world, we want to talk about the shrinking thermal load in homes relative to the amount of air that's being supplied in homes. So in the past, looking at this top case, you might have installed a 5-ton air conditioner in a typical 2,000 square foot home that was blowing 2,000 CFM. Now, as we continue to improve the thermal envelope, the size of the air conditioner is getting less. The amount of airflow being supplied to those rooms is less. We're stepping down to, say, a 3-ton system or even a 1.5-ton system, but the floor area is the same. We're still dealing with the same 2,000 square foot home. So this is one of the significant challenges that's causing comfort problems. We're dealing with less air, the same floor area. We have to be more smart about how we're using that air to provide comfort in the home. So here's some data that we've plotted from a recent study. Both of these homes are high-performance homes. One of them is, in fact, a passive house, which is a super insulated home and should prove to be very, very comfortable. But what we found was that even in a passive house, you can have temperatures well beyond that specified plus or minus 3-degree temperature range because the HVAC system isn't responding to the unique thermal loads of individual rooms. And so there's an opportunity here really to improve the way systems are designed, installed, and as we mentioned before, there's a need really for flow based on the season. That in a passive house, especially, you can end up with significant solar heat gains, and that's one of the design elements. You're trying to maximize your solar heat gain in the winter, but what can happen is if the heating system is still supplying the same amount of air to that room, you can end up with significantly overheated rooms.
Yeah, and this is these two homes are both in the same community.
Yep.
And this is a perfect example why Ibicus believes that energy efficiency does not equal comfort. These two homes are pretty high levels of insulation and air tightness. So this is one area that we're trying to dig into, further understand comfort conditions in low load homes.
Yep. Yeah. So as we said before, air delivery is key. We've gone from these big ducts, lots of CFM, and we're just naturally, as loads are going down, reducing the amount of airflow. So as a result, these duct systems, these air delivery systems need to change to continue to provide maximum comfort. So next, we're going to look at the case study of the townhomes. So this project was conducted in Denver, Colorado. It was in the Stapleton community, and these townhomes were built by Newtown builders. What we wanted to do in this study was compare the performance, again, of one of these small diameter systems to a traditionally designed and installed system. So we looked at a case where we had 3-unit townhomes. So there were a total of 6 homes that we studied in 2 separate units. And the data that we analyzed was from the cooling season. So to go a little bit more into the details of these homes, again, you see that there were a total of 6 units, 6 homes studied. They were on the same street. The 2 buildings were side by side and in the same solar orientation. So this is really a great case where we've minimized the number of possible differences between the homes, and we can really start to understand the relative performance of, say, a small diameter system to a traditional centrally ducted system. In this project, we also looked at installing mini-split heat pumps. I'll get into perhaps some of the reasons, but we weren't able to analyze the data from that house because it was unoccupied for the entire study period. And so each of these homes, as you can see in the picture, were 3 stories tall. One of the issues that the builder was encountering was with this 3-story townhome, there was a significant amount of temperature stratification between floors. And they wanted to find an efficient system which could provide better comfort and also allow them to bring ductwork into conditioned space and also maintain the efficiency level that they are expecting. So we go into some of the home specifications. Each of these homes, the installed system was between 1.5 and 3 tons. The design loads were between about 1 ton to 1.5 tons, and then that equates to a square foot per tonnage of around 1,000. So older homes, you might have had a square foot per tonnage of around 400. What we're talking about here, these high performance homes, is closer to 1,000. So that's a pretty significant change with these high performance homes. And again, just to reiterate, we had the 3 cases, B1, B2, B3, where this was the builder's standard home, putting in their standard heating and cooling equipment. And in case A1, A2, and A3, we looked at small diameter systems and also mini-split heat pump. Each of these homes was built with the same level of insulation, right around IECC 2012. So there's no differences in that regard.
So I want to just talk about the differences between the air distribution systems between the traditional home that had traditional ductwork versus the small diameter home. So the traditional home, which were the B models in the floor plan that Andrew went over, is basically a traditional ductwork, sheet metal. The equipment is located on the main level of the home, and then basically trunks that distribute through the 2nd floor, and then larger distribution branches, and then branch ducts that actually went to the exterior of the wall. So conventional thinking of trying to wash the exterior walls with conditioned air. So very traditional, a lot of chases that occupied architectural living space. So this was a standard that they wanted to understand what is the better scenario to improve comfort. So the small diameter high velocity system that the other several homes used was very small diameter trunks. We located the air handling closet on the 2nd floor, and we basically distributed up and down from there. So very small compact duct system, so really short supply and return trunks and really short branch ducts. So the strategy here is how much less ductwork can we use, and how far can we throw this air to the exterior walls to continue the throw of air. So This is just a picture of what we did to keep ducts in conditioned space. So you'll see the round, larger duct is really the supply coming up to the 3rd floor. And you'll see we basically did a drop ceiling and a closet, about 10 inches to fit in this trunk, and then really short branch ducts to throw air to the exterior walls of the room. And just to note, the duct branch size were 2.5 inches. So we're going from 8 to 6 inches down to 2.5. So significantly reducing the size of the air distribution system.
Yep. So next we'll dig into some of the performance differences between these systems. So again, the builder was concerned about stratification between floors in these 3-story homes. And we wanted to see if this small diameter system could perhaps improve upon that performance. So what we've done here is plot the room-to-room temperature difference again of each of these homes over time. And so the higher the room-to-room temperature difference, the worse the performance is. And again, that magic number that we're targeting in the cooling season is 6 degrees Fahrenheit. So any period in which these lines are beyond 6 degrees represents, a failure of one particular comfort metric. And what we see here is that, one of the worst performing homes is B3, and there's times, and so that's one of the end units. And there's times whenever that home is actually, the top floor is 10 degrees or more warmer than that entry level. And that's what the builder was trying to avoid. So we kind of verified that, yes, there is perhaps a problem with some of their central systems. Now, if we also look at that middle unit, B2 and B3, we see that B2, for example, performs a little bit better, and then B3 is performing, perhaps not quite as well. But B1 actually does perform similarly to the small diameter system. So the 2 cases of the small diameter system are the solid blue line and the solid green line, A1 and A2, and most of the time, those homes actually have the best uniformity. There's a few spikes in there, and that might have various reasons. Perhaps they opened a door. We don't know exactly. But on average, those homes did perform better. To talk a little bit about home A3, so that was the mini split heat pump case, and that's the red line. We see that it also appears to have pretty bad temperature uniformity, when, in reality, if you think about it, what we did was have a total of 4 head units in this home, 1 on each floor and actually 2 on the top floor. So in theory, that top floor could be very, very close, within 1 degree, say, of the bottom floor. What happened was that home wasn't occupied, and the thermostats were set to very different temperatures. And one of the thermostats was actually set to 80 degrees. And so that's why you see this pretty significant temperature difference in that case. So again, I wanted to show the data on this psychrometric chart. I'm not going to get into too much of the details, but what we're seeing is some pretty significant differences from the measured data to perhaps what you might expect just based on that comfort box. And then I want to dig in a little bit now to the room to thermostat temperature difference. And so what we've done here is to actually plot in each of these cells the thermostat temperature for that home against the room temperature in one of several rooms. So we're looking at the entry level, we're looking at the foyer, then we're looking at the master bedroom and one of the other bedrooms, and we're looking at how the temperature in those rooms compares to the thermostat. Now, again, according to the ACA standard, it should be within 3 degrees of the thermostat. So if that room is too warm or too cool, we'll see it on this graphic. And so the top 2 cases, A1 and A2, are with the small diameter systems. And we see that, there's some occurrences beyond that plus or minus 3-degree temperature band, but in general, those rooms are more comfortable. Now, for example, this bedroom 3, that room did face, or bedroom 2 did face south, and so it's likely that that's why this room showed more failures than the other rooms. And then to look down at the builder's standard system, there was one case in which that system performed pretty well. So it's possible maybe that this system was, just had the right installer on the right day, and the stars aligned, and it worked the best. But then there are 2 cases in which, that home didn't have quite as uniform of a temperature, and that's when we saw that 10-degree temperature delta between the top and the bottom floor. Something interesting to compare, however, is that in the case of A2, in the entry level here, the foyer, on average, the temperature in that foyer was actually warmer than the thermostat, even in the summer. Now, this is a room that faces north, so perhaps the reason for that is that it was getting more airflow in the summer than perhaps it needed. Now, in the case of B3, we see that that entry level was 4 degrees cooler in the summer. And that's a little bit counterintuitive, and it's possible that there might have been more airflow going to that room than it needed. In the winter, we might actually see better performance in that case, because if you think about it, we're supplying in the winter warm air to that bottom floor, so it's going to tend to want to rise and mix better with the rest of the house. So next we're going to talk a little bit about the energy use and how it compares between these different systems. We want to provide comfort, but ultimately we also want an efficient system. So what we've done here is calculate the total energy consumed by the heating, or rather the cooling system in each house across this 9-day period. And so that's the air handler plus the heat pump. And just to point out a couple little of anomalies, in the case of home A1, so the solid blue line, that home was not occupied for the first few days. And as a result, that system was turned off. And it looks like at the end of the day, the energy use was a little bit lower than it should have been for that home. If we normalized it, we'd see that it used a little bit more energy than we're seeing here.
Yeah, and a couple of other items that would affect the energy use of these homes would be the small diameter high velocity system. It uses a little bit more fan energy because of the increased pressure and velocity of the air moving through the duct system, and also the massing of all these homes and the volume of these homes are different, so the volume will create a little bit more of an energy load. So those are some other impacts that affect these 6 scenarios.
Yeah, and so one other thing I'd like to point out on this graphic is that home A3, so the unoccupied home, it actually had the most energy consumption. And that's also despite the fact that during the summer, some of the set points were 80 degrees for those indoor units. So why was it using so much more energy? Or we can make a couple guesses. That home had no window shades installed. And there was a decent amount of southern exposure for these homes. All of the other buildings were occupied, and they had blinds or other shades installed on the interior of the home. So that might have made some impact. And then also, in a climate like Denver, you do have some cool evenings, and it's possible that the occupied homes were able to take advantage of natural ventilation, that they could open the windows at night, get some free cooling, and turn off their systems. And of course that wasn't the case for the unoccupied home. But I think it does highlight an interesting need for shading and the impact that that can have, which might be pretty significant on energy consumption in a home. So to look at a summary of these, we can look at the room-to-room temperature difference. So the bottom line on this table, if we compare home A1 to home B1, we see there's a slight performance improvement on home A1. It was 2.4 degrees different on average relative to 2.6 degrees. And home A2 versus home B2, it's a little bit more stark, where home A2 only had a 2.1 degree temperature difference versus 4.8 for home B2. You know, the energy consumption, like we were saying, was similar. You know, of course, with a small diameter system, you're going to use a little bit more fan energy. But what we found was that it wasn't that much different. So next, we're going to talk about our home run manifold system.
Yeah, and so this is, Andrew's going to talk about some of the work we are doing at investigating air delivery strategies with utilizing smaller diameter ducts. So like Andrew said, over the last half hour, you know, low load homes is the trend. That means we're using a lot less energy in the home, which means there's a lot less airflow in these homes, but we still have the same volume of space in these homes that we have to condition. So we're focusing on how to bring air delivery to each of these rooms effectively, and also how do we maintain comfort in each of these rooms with a smaller volume of air distributed. So some of the things we're looking at is sort of potentially similar strategies to what the PEX water industry has looked at over the last 15 years, where they looked at, you know, remote manifolds of distributing water. Well, think of water as air. Could we use the same sort of methodology to bring air to these homes with smaller pipes? The other thing we're looking at is what are the challenges with different duct materials? We know there are challenges with the codes today with thinking of duct materials that are beyond fiberglass or beyond sheet metal. Those duct materials today, like flex duct and sheet metal and duct board, meet the code standards, the UL 181 and ASTM E84. So we're looking at potentially other materials that could fit in this space of small diameter ducts. There is a lot of value to this. Our builder partners, they see the value in small diameter ducts because it helps them potentially standardize duct layouts, and also helps the trades effectively install duct systems in homes. Typically today we see a lot of ductwork in homes very sporadically laid out, very ineffective, and which potentially causes comfort issues. So we're trying to crack this nut. If you think of ductwork in home, it is the bastard stepchild in home building. No one really thinks about it. So we're trying to attack it to try to make it better. So that's what we're really focused on as Ibicus. So Andrew's going to talk a little bit about what we've done over the last year and what we continue to do, or continuing to do in the next year or so.
Yeah, so if you think about this traditional duct system that nobody really wants to think about, historically the way these are designed is to go through a series of design manuals, and you calculate the load on the home, you size your system, and then hopefully at least you start to think about the duct design. And the way that is designed is you have many different sizes, diameters of duct runouts, different sizes of branches, and ultimately the idea is that by reducing the size of your trunk as you take more and more takeoffs, you're able to hopefully maintain the airflow that you want to those longest runs. Now, the chances of one of these systems getting designed correctly poses some risks. The chances of one of these systems actually getting installed correctly is even more of a risk. And so we're trying to look at a different methodology which perhaps eliminates many of these risks. So like Anthony said, we're considering this home run manifold system. So instead of sending one duct to a room and specifying that that's a 4-inch by 8-inch register and everything, instead, what if you designed it such that you had 2 or 3 ducts of the same size? So you're always using, say, a 2.5-inch duct, and you know that that duct gives about 20 CFM, then you can significantly decrease the amount of effort required to correctly design that system. So that's what we're trying to understand here is, with this home run scenario, can you get that predictable airflow out of that duct, and under what set of ranges can that be the case? So we're going to look at a little bit of data here and discuss the impact of that. So again, just to be a little bit more clear, we have this little cartoon comparing the traditional duct layout, where you often have your ductwork outside of conditioned space. You have a big air handler, and it's very challenging to actually get the airflow that you need to those specific registers. And once your airflow gets there, it's gone through so much ductwork that it might not even be the temperature you want. And so if we compare that then to the home run manifold system, which can be located much more centrally in a home, your duct runs are ultimately shorter. And if they have a smoother duct material, you actually eliminate a lot of the static pressure just by shortening those runs and having that smooth material. So one of the things that we did in this study, so actually what we did is we started by looking at different manifold designs. And we're not going to get into the details and the results of that, but I want to discuss a little bit this mock-up case, where we picked the best manifold design in which we had this nice even row of outlets coming out of that manifold and connected to this ductwork. So the ductwork layout that you see here was designed for the second story of a large home. This was about a 2,500 square foot, maybe 3,000 square foot home, and we decided that for a home that big, we really needed 2 of these systems. And so we wanted to see how it would perform if we considered one system on that top floor. And so you can imagine this duct system, if it's laid flat right now, but if it were unfolded the right way, it would actually fit into about 4 rooms for the top floor of that house. So what we wanted to look at was the relative airflow coming out of those different duct runs. And we understood that this was going to kind of be an extreme case. One of those duct runs was only 5 feet. One of those duct runs was 36 feet with a number of elbows. So that's a total of about 8 times longer of a duct run. But what we found was the airflow was 24 CFM in the 5-foot case and 14 CFM in the 36-foot duct case. So not quite half the airflow for a very significant change in duct length. And so, if we eliminate some of those kind of extreme conditions, what we found was that the airflow coming out of those duct runs was within about 20% of each other. So if we said, perhaps the minimum length is 10 feet and the maximum length is 25 feet, there's about a 20% spread in the total airflow coming out of those ducts. So we think that there's a lot of potential to this system. Some of the other important factors that we were considering was the total static pressure of that system, and at 51 pascals, not that significant. And then one of the other metrics that we looked at was the total CFM we could supply with this system. So we took an off-the-shelf ducted mini-split, connected it to this system, and we were able to get 176 CFM through that ductwork. Now that system was designed to supply 250 CFM. This was a 1-ton ducted mini-split. So it definitely reduced the CFM, but we think there's some potential here by putting in a slightly more powerful motor, perhaps, that you could get that airflow that you need. So one of the things we did to understand the potential there was to actually connect a booster fan, which in this case was a duct blaster. We connected this to the return plenum of that system, and continued to ramp up the airflow to higher and higher CFMs. And then we measured the static pressure in that plenum to see how it would compare. And so what we're looking at here in this chart are two different types of curves. The black curves all represent fan curves. If you just had an air handler sitting out in the open and connected different duct systems to it that had progressively more and more restriction, you're going to naturally get less and less airflow. So that's why on the black curve, as the CFM is reduced, the static pressure increases. And then the red curve represents kind of the other half of the story, the duct system. And so the red curve represents, if you had different fans connected to the same duct system, what kind of airflow are you going to get? And the intersection of those two curves is how any particular combination of systems will perform together. And so what we found was, down there at the bottom range of that system, when we just connected it to an off-the-shelf ductless or ducted mini-split, the static pressure was around 0.2 inches of water column, and we were getting that 176 CFM of airflow. But if we continue to ramp up that airflow, we're getting a little bit more static pressure. But at around 250 CFM, we're still below 0.4 inches of water column, which for many air handlers is a reasonable number. So we think that there's a lot of potential to this system, and looking at the static pressure, which is really perhaps one of the significant challenges with this system, or we thought it would be a potential problem going into this project, we've actually found that static pressure isn't as high as we thought it would be, and we're able to get the airflow we need without really cranking up that motor and burning a lot of extra energy.
Yeah, and I guess the other things to note on this graph is you saw the picture of our mocked up duct system. We used PVC pipe. This is not a duct pipe, but it has a very smooth inside wall. We believe that has an impact. We believe, and the duct system was really airtight. So these are some little things that may tell us a little bit more on why we're getting some of these results.
Yep. Yeah, so a summary of findings for this particular project was that, we found the manifold system did actually show predictable airflow out of those outlets. Was it always the same? Were we always getting 20 CFM regardless of the length? Well, no, but that's to be expected. However, we did find that the airflow isn't that far off if you establish a reasonable set of design requirements. Again, the static pressure was minimized using that smooth ductwork, and also what's important is the compact duct layout. By routing ductwork through floor cavities, even through interior partition walls, you're able to get the ductwork right where it needs to go at the minimum length. And so that's one of the, really the big advantages of this system, is being able to bring your system into a very compact area, and you're actually also minimizing the impact on perhaps other livable area by using some of the existing cavities in a home. We did find that the system can supply enough airflow to meet the demand for a low-load home. Larger homes, you might need to start thinking about perhaps 2 of these systems. But if you're thinking about it as a mini-split, it's not inconceivable to have 2 or multiple indoor units and a single outdoor unit. And then something else that we've thought about with this system is, because you're running all of the ductwork back to that central location, you actually have a lot of potential for seasonal balancing to get the exact airflow you need into a particular room. And this is something that, the existing method is to install balancing dampers. Typically, they should be installed right after a branch comes off of the trunk, the main trunk of your duct. Well, where is that system? Where are those branches typically installed? Maybe in the attic, maybe even within a wall cavity where it's inaccessible. So once that system has been installed, it's impossible to go back, or very difficult at least, to go back and make changes. Whereas if you have the ductwork all coming back to this one central return, just like that PEX manifold, you could pretty easily make changes to the balancing. So we think there's a lot of potential there for improving comfort for homeowners.
So where is Ibicus focused on in the future? So as Ibicus, we're committed to a lot of the focuses that Building America has created for us as an industry to look at. So I just put up a slide showing the optimal comfort systems for low-load homes roadmap for the next 5 years. So the outlined areas in red are two areas that we're committed to look at. One being the development of design procedures and tools and comfort metrics for low-load homes. So a lot of the data and work that Andrew has just shown us is in that area. And then we're looking at validating and demonstrating these metrics and these systems for low-load homes in the next several years to come. So two areas that we're going to continue. So the plug-and-play duct system is an area that we see a lot of opportunity. A lot of opportunity for the industry to get better at, specifically our production home builder partners. They see the value in it. So we're committed to accelerating the level of effort to get to a point where we believe we can design a system that's smaller diameter that'll effectively maintain comfort in low-load homes. And then we wanted to understand what the time and motion study is for a small diameter install versus a traditional. We believe there's a lot of cost savings, potentially a lot of cycle time savings in the field. So we're going to also look at some modeling exercising to continuing what we're doing and looking at opportunities for home run manifold systems or potentially remote manifold systems. So we're going to continue that the development of small diameter ducts. And then the second one is, we hinted at it, but we are actually going to be putting together a white paper for Building America looking at a comfort rating method. So similar to the HERS rating method, where there's a score of 0 to 100 that rates the home's energy performance. Going back to that energy efficiency does not equal comfort, we believe the industry does require a comfort metric that could go side by side with the HERS rating, and we can get better, give better information to a homeowner and potentially a builder to differentiate their built home to a homeowner when they're trying to purchase one. So a homeowner can see both scale and say, okay, I have a great energy performing home. Oh wow, I even actually have a better comfort rating for this home than that home builder across the street. So we're trying to develop a methodology and understanding. And the areas that we're looking into, obviously we're going to look at ASHRAE 55. How does that standard reflect a new metric? We're also looking at the ACA RS standard, but there's other factors that we have to consider that potentially these current standards don't talk. So architectural design, massing of the home, how many stories, they're very impactful to maintaining comfort, not just in the home in general, but in rooms of the home. Enclosures is very important. I think as an industry we've done a decent job of getting better enclosures, but we also need to look at what the impacts of enclosures are to the mechanical system. So, enclosures are basically very good right now. They're going to improve a bit, but I think the gap is the mechanical system to maintain that comfort for those really high-end enclosures, because the capacities of these equipments are basically a lot smaller. In some cases, 3/4 of 25% of the traditional size. And then the last part is occupant behavior. You saw Andrew talk a little bit about the occupants. They vary from house to house, neighbor to neighbor. So we need to understand what are the effects of occupancy on creating comfort conditions. So that's what Ibicus is focused on, at least for the next 3 years. So any feedback that we can get from the industry and anyone listening to this webinar, we'd be more than happy to listen to you guys, because that could help us get a better understanding of what we need to do.
Yep, thanks again for listening, everybody. I guess at this point we'll open it up to any questions.
All right, great. Thank you so much, Anthony and Andrew, for that. So we have a whole lot of questions, and we are not going to be able to get to them all. So if we can't get to your question, we will try to address that over email after the webinar. So going back to the basis for thermal comfort section of slides, we had a couple questions there. Someone was wondering, do you consider that having more humidity adds to discomfort at a lesser temperature difference? So if the home's humidity is high, temperature difference is felt more by the occupant versus low humidity and temperature difference not being felt. Was that a consideration?
Yeah, I mean, that might be a possibility. That's not something we were specifically looking at in this study. You know, that's getting into pretty detailed level of analysis to see, you know, maybe at 80% humidity, the temperature band should be 2 degrees or something, and whereas at 50% humidity, that temperature band should be 3 degrees. That might be the case. That's just not something we were really looking at.
Okay, great. And then there were a couple questions about whether there was mechanical ventilation provided in those projects, exhaust or...
Yeah, and so in that case, we were looking at a total of 4 different home builders, and each one used a slightly different strategy, but there was mechanical ventilation provided in those cases.
Okay, great. And then do you have an explanation for the low RH in homes 3 and 12 in the humidity plot?
Yeah, I mean, I can try to flip back there real quick. Let me just zip all the way back. Yeah, so, you know, in terms of specific homes, you know, there's many different factors that could have been causing that. So we're looking at homes 3 and 12. Let me just bring this up again. Yeah, so the significantly lower humidity, again, we don't have specific reasons. We could make guesses. I don't have all of the various differences between the homes displayed here for us. But it could have been, you know, perhaps differences in ventilation strategies or something. But again, we don't know specifically.
Okay, great. And then you can move on to the comparative modeling section. Someone said, your statement that all of the homes measured were able to maintain an RH of below 60% without dehumidification, is this due to the fact that these homes are using AC during the measurement period?
Yeah, so the homes were all using AC during the measurement period. You know, again, when we're looking at this, there were 2 homes that perhaps there was a humidity concern. We were making some guesses as to why that might be. But yeah, all of these homes were using air conditioning throughout this process. We measured one of the supply ducts. We put a temperature sensor in that supply duct so we could see when the system kicked on. There were a few periods perhaps of vacation. You know, for example, this home 28, we see that magenta region. That was actually a period of vacation when the system wasn't running as much. Otherwise, these systems were running.
Okay, great. We had a question about how do the mini split heat pumps do with respect to humidity. The question asker is in Nebraska, where they see a lot of oversize associated with that type of installation.
Yeah, so I guess this is perhaps considering the comparative modeling study, and humidity wasn't something that we were really digging into. You know, I've heard also mixed results that oversizing those mini splits might potentially, you know, have impacts to the humidity in those homes. But again, that's not something we're specifically looking at in this study.
Okay, great. And then one more question about the comparative modeling is someone was wondering, was the basement finished and what was the ductwork like in the basement?
Yeah, so the basement in that case was assumed to be a finished basement, and there was supply air going to that basement. I haven't included it in these plots. You know, just there's only so much space but those were conditioned basements, and actually the data from that is included in this room to thermostat comparative analysis.
Okay, great. And then moving on to the multifamily case study section, someone noticed that you had insulated the ducts within the conditioned space and noted that many builders do not insulate ductwork inside of the envelope. Is this typically done only with the small diameter systems?
Yeah, so in a high velocity duct system, typically the air temperature is a lot colder. So some of the concerns from the manufacturers is they want those ducts insulated even though it's in conditioned space. They're concerned about condensation forming on the duct material itself.
Okay, great. And then we had a question. A concern of the project was air stratification between floors of the homes. Both small diameter and traditional systems use riser ducts, which are historically notorious for not being well sealed, which can lead to stratification. Was there a consideration of building a more well sealed compartmentalized floor as a way of improving comfort?
Yeah, and so in this case, that's definitely a real concern. But we were really focusing on the differences in performance of just the air distribution system, kind of stock, how it's installed today. So that would be another interesting area, I think, to explore.
But I believe the duct systems were sealed to as best as we can in these homes that we monitored.
Yeah, so we have the measured duct leakage in this table. And now I didn't get into those numbers, but you can see the traditional system actually had a pretty low measured air leakage. We're talking 5 CFM at 25 pascals. Now the small diameter system actually showed worse air leakage, so around 50 CFM at 25 pascals. There's a couple reasons for that. So that traditional system, was installed with mastic and everything. There was more potential to seal that ductwork. Whereas, as you saw with the small diameter system, these branches are connected with a foam gasket to that trunk, and so there is no mastic there. So it's possible that you get a little bit more leakage around those various joints. So that was one difference in these duct systems.
And we always want to see airtight duct systems.
Yeah.
Okay, great. So we had a couple questions about noise difference or draftiness when you're looking at the home run manifold system. One person said that fast-moving air is one of the chief sources of occupant comfort complaints in office buildings, and how do we avoid repeating the mistakes made in that sector? And then we had another question about whether there's any noticeable noise difference or draftiness with these systems.
Okay, yeah, so I think I'll answer the noise question first. And that's something we were concerned about as well. You're putting this rigid ductwork in. Are we going to get significantly more noise? So far, we've only conducted tests in our warehouse, and we basically weren't able to hear the duct above just the background noise of various other equipment in our warehouse. We tried to put that meter up there about 3 feet away, and we didn't actually measure any noise. So one of our next stages with this project is to install that system in a house, in one of our test houses, and we will be looking at noise performance. So in that isolated case, we'll be able to get better numbers. But our initial thoughts are that the noise performance isn't going to be a major detractor to the system.
Yeah, I would say the only noise issues potentially at the actual air handler, especially if we're building up a little bit more static. We may get a little bit more noise from the fan. But as of today, we haven't seen any increased noise levels from the termination of the duct.
Yep. And so the other question was related to airflow and draftiness, and if the airflow is actually hitting a person or hitting an occupant, yeah, they might perceive that as being uncomfortable. And that's definitely a risk with these smaller systems that are emitting more of a jet type airflow. I think that that's an area that is definitely ripe for more study, And whenever you're designing one of these systems, you do have to be very careful with where you place those registers so that you're not blowing into potentially occupied spaces.
Yeah, and as you can see in this picture, we're always trying to locate these diffusers at as close to the ceiling as possible. So high sidewall is the best location for distributing air in a room. So we can get that effect of throwing air across the ceiling to mixing better, and it won't be at someone's face. Yeah,
so the idea is, you're probably not going to use, for example, a floor register or a lower wall register as much as possible, these high sidewall registers.
Okay, great. Thank you very much. I think that's all the questions we have time for right now. Like I said, we will try to address some additional ones offline. We'd now like to ask our audience to answer a couple short questions about today's webinar. Your feedback will help us know what we're doing well and what we can improve. So please participate. The first question asks whether the webinar content was useful and informative. Please take a moment to choose your answer. All right. The second question is going to ask about the effectiveness of the presenters. And the third question asks whether the webinar met your expectations. Okay, thank you so much for answering our survey. The next Building America webinar is on December 16th. It will focus on solutions for combustion safety in existing homes. You can also subscribe to receive notices about upcoming webinars and other news at the URL on the screen. On behalf of the Building America program, I'd like to thank our expert speakers for their time today and our attendees for participating in today's webinar. We've had a terrific audience. We very much appreciate your time. Please visit the Building America website to download a copy of the slides and learn about the program. We will also have a recording of this webinar available there within the next couple of weeks. We also invite you to inform your colleagues about Building America resources and services. Have a great rest of your day, and we hope to see you again at future Building America events. This concludes our webinar.